let's make sure that we are in focus. Okay. So this is going to be interesting because there's a projector here, which means two things. One, whenever I do this, it will block. So I will try to do that less than usual. Two, my pointer will actually work on this, which is really cool. It means I'll be doing less of this and trying to reach. There's also only the one. It's a little smaller classroom. Let me know what you guys think of it. It's free during our usual time. If you like it more, maybe we'll switch. Because I think I might like it more, but we'll see. Of course, now I've been used to holding this in a way where the pointer wouldn't work. I'm gonna have to change everything. So anyway, okay. So today, we're gonna have a quick kind of review and also pushing forward in a more advanced way of two topics we've already covered, where and closures, because those are going to come into significant play here for our upcoming discussions on concurrency. This is going to be hopefully like a little bit of a lightning kind of faster lecture. I'm going to set my watch to a 20-minute timer. I'm going to try and get through it that fast. We'll see. Because what comes after is much, much, much longer. So, cool. Okay. Advanced use of the where clause. We talked about the where clause. It's something you can use for generics and for associated types and for protocol conformance and all sorts of cool stuff. And we'll talk about all of the kind of more advanced uses that we didn't cover here. So, one thing I'm noticing is that it's a little more washed out color-wise here. How do folks feel about that? Is that visible? Can you see it all okay? Okay, cool. Yeah, that's just me. I like strong contrast, but we should be fine. Okay, so let's talk about generic constraints. So here we have the start of a function definition. This is a function that's going to check to see if two collections that are passed in are the same size. It's very similar in structure to the function that we were kind of looking at for the quiz. It's a little different. We have two types specified, T1 and T2. So in this case, because we're using a T1 and a T2, and you can probably guess what comes next, we define two parameters of type T1 and T2. So in this case, these generics don't have to be the same. They just both have to conform to collection, right? So then you return a bool. Cool, that's great. Okay. But let's say that we wanted to add a further constraint here. Like, let's say that we wanted to say not only that T1 and T2 both must come from a collection, but let's say that we also wanted to say that both must also, I don't know, have the same kind of element, right? Or that their element must be an int or something like that. And basically say, yeah, we want this to be any kind of collection, right? An array, like a set, right? A stack, if you implement your own, collection as a stack, right? But we want the element of that collection to be an int, right? And you'll recall, or you might not recall, but I will tell you that collection, the protocol, has as one of its associated types, element, right? And that is the type of the element, right? So you can add something like this, right? Where t1.element equals t2.element. So now we're saying, cool, okay, so these two collections can be different types. They can be a set and an array. They can be an array and a stack. They can be whatever, as long as it implements collection. But the two instances passed in, they must both have the same generic element type, right? So they must both have the same generic type element. It must be equivalent, right? So what that means is that this function will only be callable if the two collections that you pass in both have the same type for the items within those collections. So then you can just do something cute like this, right, where you say c1.count equals c2.count, right? Because count is something provided by collection, right? This is kind of a useless function, but it's fun. So, all right. So let's take a look. Here's a few options here. These are all arrays. We're not really utilizing the true power of this function, which is that it can compare different kinds of collections, but it still shows kind of what the where clause is going to do for us here, right? So here we can do two different calls to same size collection. The first one, we try to pass in strings1 and ints as our two parameters, and we will get an error there. The second one, we will pass in strings1 and strings2, and we will get back a value of false because those collections are not the same size. Strings1 only has 2, and strings2 has 3. The error, of course, here is type of expression is ambiguous without a type annotation, which is useless, but it is the error you will receive. That was weird. Okay, so you can also use where to apply multiple constraints rather than just one. So one thing that you can do is use a comma in between your elements and where, or between your constraints and where. So you can say, wait, I've got a pointer, right? You can say t collection, right? And so T must implement collection, okay? Must adopt and conform to collection. And the associated type element, right, on T must adopt and conform to equatable, right? Now T has access to this associated type element, even though we don't define it anywhere here, because that's an associated type on collection. And by this point in time, we've already told the compiler, hey, T conforms to collection, which means it has an element associated type. So because it has an element associated type, we can say, oh, cool, we also require that its element associated type be equatable, right? Which means that this function is callable upon when you pass in to it a collection that, A, conforms to the collection protocol, and B, the elements of the collection also conform to the equatable protocol. So then we can do some stuff, nasty stuff like this, where we check the first item in the collection and the last item in the collection. Please ignore this gross index syntax. It's how collections access the last element, and I hate it. I don't like it. I don't like how collection does that. I think it's silly, but it's what they do. So then you return first equals last, and we're getting a Boolean back saying, oh, the front and the tail are the same, right? So here we can pass in this. This is an array of ints. Ints are equatable. That is something that is defined as a part of ints. They conform to the equatable protocol. So here we get false for the first one because the tail and the front aren't the same. Here we get true because the tail and the front are the same. And then, interesting. Okay, I thought I had an error version on there, but I guess I didn't. Basically, if you tried to pass in a collection of a type that doesn't implement the equatable protocol, you'll get an error, a compiler error, rather than a runtime error. So it'll let you know. All right, so here we have where on custom types. So for our own custom type, like stack here that we're implementing, right, we have this stack of elements, right? So our generic type parameter is element, and then we can put the constraint where element is equatable. You could also do this without the where keyword. You could put that, inside. You could say element colon space equatable, and that would do the same thing. But this way, it's kind of out here, and we can mess around with it and do other things with it. So here we have our stack. It's an array of elements. We have this function all the same that's going to go through and check to make sure that they're all the same, and we can do that because we know that element implements equatable. And if it didn't, then we wouldn't be able to perform this not equals operation if element not equals first. That's only available to you if the type of the two things on either side of that operator are equatable. So now that we know what that looks like on the inside, we can take a look at some callers of this, right? Now you'll note we've defined up here this cute little empty struct called non-equatable. It doesn't do or hold anything, but the key thing to note, it could hold whatever. The key thing to note is that it does not implement the equatable protocol, right? Now, I should have used a class because structs can be kind of weird. Sometimes, like, structs can sort of synthesize some of the most useful protocols, like equatable. So if a struct is made up of stored properties that are all already equatable themselves, then it becomes equatable, right? That's just something Swift does. It's handy and fun for you, makes it easier to do things. So that should be a class, pretend it's a class. But anyway, so here we get this error. Generic struct stack requires that non-equatable conform to equatable when we try to just instantiate a stack passing in an array of non-equatable types. And that is because they are not implementing equatable. So you can also move that generic constraint onto the function all same, which is pretty cool. Now you are referring to this element type parameter, generic type parameter, even though it wasn't defined on the function, because it was defined on the struct. Anything within this scope for the struct can use the element type parameter. So now we don't require this at this element is equatable at the constructor level, which means we can build a stack of non-equatables. We just can't call the all same function. So instance method all same requires that non-equatable conform to equatable, right? And so what this means is this stack and this stack have different abilities than this stack, because this stack doesn't have access to this function. And that can lead to conditional conformance, which we're going to look at shortly too. Or I think we might have already looked at, I can't remember. Anyway, you can also do where on extensions. So you can do any where clause that you would do on a struct or a class or whatever. You could also do it on the extension as well. That's totally fine. And then everything defined within that particular extension only happens if the constraints are true for that particular instance of the type. This means that you can take a bunch of logical pieces of a type that you want to exist for different constraints and break them up and say, oh, okay, so if element is equatable, then we can do all these functions, put them in this extension. And if element is hashable, then we can do all these functions, put them in this extension. And then you just do it like that. So you don't have to define where on each single function. Yeah. And so here we're able to define this because the where is on the extension, and then we get this error. Instance method all same requires that non-equatable conform to equatable, right? Yeah. All right. So you can also do this thing for specific types. So you don't just have to declare a constraint as conformance. You can also declare that it must be equivalent to a particular type. We saw this earlier when we were comparing the type of the two collections that were passed in. We wanted to make sure that their elements were equivalent. Here, we're just straight up saying, oh, element has to be int. So we can actually say, oh, stack, it's this really cool generic thing. It's got all these cool generic things it's doing generically, but I want to add something to it that only works if it's a stack of ints, right? If it's a stack of ints, then it can do this all same function, right? So that's something that you would do maybe if int had some functionality that you want to, do some query on that no other types tend to have. Okay, so using where for specific types to conditionally conform to a protocol. This one's interesting. So basically, we have this stack, cool, it's got element, dope, right? All that. We still have our non-equatable struct, that'll come into play. We have a new protocol. It's called hasInt, okay? This protocol, basically, what we're saying is, oh, this protocol, if you implement it, then you get access to this function, right? Here, in this extension, we say that, okay, so we want stack, the type stack, to adopt the hasInt protocol only when its element is int. So only if the stack has ints within it does it adopt and conform to the hasInt protocol. This has a lot of really weird implications. It's kind of the weirdest, most interesting thing you can do with associated types and protocols in Swift. It's very hard to do something like this in, say, Java or C# because of how inheritance and interfaces work there. But in Swift, this is a very common pattern, where you just add functionality and you add conformance to a protocol in a conditional manner, right? Oh, this instance is only a hasInt if its elements are int, right? So yeah, which means, of course, that when we try to call myStrings.AllSame here, we will get an error. Referencing instance method allSame on stack requires the types string and int be equivalent. That's a little bit more useful of an error message than the rest of them have been. Basically, it's saying, oh, this type string that's on my strings, which is currently what the placeholder element is for that particular instance, the myStrings instance, needs to be an int, not a string. If ints and strings were equivalent, right, if those types could be considered the same thing by inheritance or something like that, there wouldn't be an error. Okay? Cool. All right, so you can also use where clauses on associated types. So when you define an associated type inside of a protocol, you can constrain it with a where clause. So let's take a look here. We have two protocols. The first one is stackable, and it has an associated type of value, and it has a property requirement of value of type the associated type, right? Then here we have this protocol stack, okay? And so stack is going to have its own associated type element, just as we've seen before, but now we're going to require that element conform to stackable. And we're going to say where element.value, which we defined here, right? So because element is stackable, it has access to the stackable associated type, okay? So where element.value, and that's here, adopts and conforms to the numeric protocol. Numeric is a protocol that's defined by Foundation. It's just like ints and doubles and all that all implemented, right? Basically, if it's a number, it adopts and conforms to numeric, okay? So basically here, we're doing something similar, but instead of int, we're saying, oh, doubles, ints, whatever. Yeah. So then we can add our stack function, requirements, etc., right? But basically here, what this is kind of saying is that if the element that you pass in implements stackable, then you can only use that element if its value is adopts and conforms to numeric, right? Otherwise, you'll get a compiler error. It won't let you compile, okay? So this is basically a way of very strictly defining what people can use as your associated type. You can put these huge constraints on the generics and associated types that users are allowed to use in your API. This is really important and helpful for API design when you're building libraries for other people to use. It ensures that your code doesn't do weird, nasty things, and you don't let them do weird, nasty things with your code. It also gives you access to the numeric protocol. So inside of any implementer of stack, any concrete type that adopts and conforms to stack, whatever type you use for element, because it's guaranteed to be numeric as well, or sorry, element.value is guaranteed to be numeric as well, then when you call .value on, let's say item gets pushed in, right? We have push item element, right? In our implementation, we'll say, oh, cool, item.value, which we have access to here, right? And the type of value we know is at minimum numeric, right? That's pretty cool. It also means that we can have stackable where value is not numeric. You could also have, for the situation I described, you could do that very similarly by just requiring here that value is numeric. You could just replace value with numeric, get rid of the associated type, right? But because we've done it this way, now Stackable can also be a generic kind of protocol around anything. Cool. Okay, sorry. So before we just move on from advanced where, any questions about any of this where constraint stuff that I went over? Cool. Okay. And it's taking a million years. There we go. So closures. So we talked a lot about closures in the functions class. We've seen them throughout our code all the time, especially trailing closures, which is a little shortcut so that you can just put the block right after the function. If the last parameter in the function is a closure, that's going to come up a lot during the discussion of legacy concurrency in Swift, which is the next lecture set. So, or the next part of this class. So just, remember how that works. And then we're also going to look at just closures in general and also something called escaping closures. So here we have our fun closure. This is a closure type. If you'll recall, it looks a lot like a function type because it is, because closures are kind of just functions that you pass around, right? And here we use that cool, fun trailing closure syntax, and I just hit the 20-minute mark, so we're nowhere near done. The trailing closure syntax, right? So here, basically what happens is we print first reminder, then we call send reminder with this closure. So we pass this closure in as the parameter up here, right? And then here we print and call the reminder, and we use the result from reminder, which is a string, right? And we print that, okay? And here is the result, because we're also using the shortcut where if you have a return type expected for a function, then if you only have a single expression inside the function, it tries to return that expression, okay? So we're using like 3 or 4 different shortcuts and syntactic sugar pieces here that Swift provides to make this much more readable than it would be otherwise. So this is going to print first reminder, then closure reminder, then last reminder, right? Wow, I got it right. That's a good thing. It would be really weird if I didn't. So let's talk about escaping closures. We didn't go over escaping closures at all, okay? That's because they're semi-complicated and you don't really need to know a lot about them until we get to concurrency, which is what we're doing today. So escaping closures are basically closures that get preserved beyond the scope of any function or method they get passed into. So here, let's go ahead and define this reminders storage class. And it's going to have an array of these closures, and these closures are going to, return a string, right? They're a reminder that returns a string, okay? So here we have this function save reminder. We have as the only parameter this closure that returns a string, right? And then here we're going to do reminders.append closure, right? So basically we're just saying save reminder, we pass a closure in and then we save it to use later, right? That's the goal of what we're doing here in the code. And the compiler immediately yells at us because it's a jerk, okay? And it says converting non-escaping parameter closure to generic parameter element may allow it to escape, right? And by escape, what it's saying is this closure has a lifetime. It has a life cycle, just like any variable or parameter. And when it falls out of scope, then it gets wiped away. There's no more references to it, and it goes out of memory, right? This is related to ARC and ref counting as well. Basically, it goes down to 0, and then it gets deallocated, right? Here, though, we're saying, oh, we're actually adding it to this array, which means the ref count goes up. So when we leave this function, save reminder function, then the ref count only goes down to 1. And so it gets retained and held in memory, and therefore it escapes the function, right? It's no longer held only within the function's scope. It has been saved by something else, okay? It's basically doing this because that can be dangerous. It's a way that you can get into a lot of trouble and cause strong reference cycles for yourself. The way we're doing it here is safer, but not super safe. So, we have a way to basically kind of tell it, yeah, we know it's escaping, we're fine with that, right? And then here's how you might want to use it, right? This should have all printed by itself anyway, but so this is how you might use it. You might save reminder, first reminder, then save reminder, last reminder, and then you iterate through and you print them, right? Obviously, this is something that would be better accomplished by just passing in a string, okay? But we're kind of, doing this for a reason. So let's just say we want to save the execution of creating the string for later. We don't want to hold it in memory. We just want to hold the ability to make it, all right? So the keyword that we use to say it's okay, we know it's escaping, don't worry about it, is, yeah, we know what it prints. Escaping. Yeah. So you say, yeah, we know it escapes by saying that it's escaping. So you just use this little @escaping keyword, and that error goes away. You say, oh yeah, we know it's escaping. The compiler forces you to do this because it wants to make absolutely sure that you know what you're doing. It's why, when I leave the house, I used to have both car keys on my keyring, and then I took the Prius one too many times. My wife struggles to drive our other car, and so I took it one too many times when she was, had an appointment, and was like, Dan, I need the Prius. It's got my accessibility thing. I have to drive that, right? So now I keep the Prius key off of my keyring. So if I ever want to take the Prius somewhere, I have to grab the key for it specifically, and it makes me stop and think. That's what the compiler is trying to do here. It's trying to make you stop and think and double check your work to make sure you're not creating a strong reference cycle, because closures are reference types, which means, and they have the ability to capture things, right? So like if this closure, for example, ever uses storage inside of it, then it captures a reference to storage. And then storage is saving the closure here in this array. And that creates a reference cycle that cannot be broken. So be careful with closures. And the compiler tries to help you be careful. All right, so we can also preserve closures and escape things rather than by preserving them by storing them inside of a property or something. If they get used within another closure that is escaping, then they are also escaping. It's a prison break. They're all escaping together, okay? So here we have save reminder, which is we've changed, or not save reminder. This is the same function. We have a new function called format and save. So now we decided that we want to modify anything that comes in before we save it, right? So we still have our closure here, right? And then now we want to just add this right here, right? And so we're kind of nesting calls deeper and deeper within more and more closures that can call further and further and further in, right? But because we're putting this reminder closure here inside here, right? It's being captured by the closure on save reminder, right? This parameter, closure escaping string on save reminder, is capturing our reminder closure, okay? As a result, it is now escaping the function, right? It's being retained by someone else. And that someone else is an escaping closure, right? If this closure wasn't escaping, if save reminders closure was not escaping, if it wasn't stored somewhere, right? Then you don't need the escaping keyword on it, and you also wouldn't need an escaping keyword on format and save, and you'd get no error, right? Because there's no risk that you're going to create a strong reference cycle that way. You're just creating a nest of closures that never have the potential to point back to something. Or they have a chance to point back to something, but they're not being held onto by it. They're not being held onto by it. Anyway, so to solve this, we just put escaping, as before. And this will compile, and it will print first reminder and last reminder. A stunning example, just something that's really exciting, right? Just printing 2 strings. Sorry, I just don't have a lot of space on these slides to make sure that the text is very visible. Otherwise, I'd do much more interesting examples. But I have to keep it really simple, so. All right, 5-minute break. That is advanced closures, that's advanced where. Why we talked about that today will be very, very relevant next lecture. So, cool. All right, now I need to stop the recording.